right, welcome to Calculus 3, video lecture number 3 on the dot product. And in the previous lessons, we've gone over how to add and subtract vectors, as well as how to multiply a vector by a scalar. So we've multiplied a vector by a real number. But now what we want to look at is how to multiply vectors by each other. And it turns out that there's actually two important types of vector multiplication that we're going to need to consider. So first, in this video, we're going to consider the dot product. And the dot product also is referred to as the scalar product or sometimes the inner product. And in this case, when you use the dot product to multiply two vectors, your result is a scalar. So you don't get back a vector, you get back a scalar quantity. And then in the next lesson, we're going to consider the cross product. And with the cross product, when you multiply two vectors, your result is another vector. So that's a different kind of vector multiplication. So first, let's just focus on the dot product, and the definition is as follows. So if you have two vectors, u with components u1, u2 up until un, and vector v with components v1, v2 up until vn, we define the dot product u dot v to be u1 times v1 plus u2 times v2 plus so on and so forth up until u sub n v sub n. So basically what you're doing is you multiply all of the corresponding components, and then you add them all together. And because you're adding them all together, that's why you end up with a scalar at the end, not a vector. Now, in this class, most of our vectors are going to be in 2 or 3 dimensional space, but this is not a necessary requirement. Notice the definition works for vectors in n-dimensional space, but just make sure that both of the vectors have the same dimension. The dimension must match. Otherwise, it wouldn't work, right, for you to multiply the corresponding components if they don't have the same number of components. So just a quick little example. Evaluate the dot product for the two vectors 7, 2, -1 and 3, 0, 4. And you'll notice when we are working with the dot product, we use a heavier dot than the dot that we typically see when we're referring to multiplication, right? Regular multiplication. So here I'm going to take the corresponding components. So 7 times 3, that's going to be 21. Then I have 2 times 0, that's 0. And then -1 times 4, that's -4. And this gives me 17. Okay. And it's fine if you do these in your head. You don't even need to write out this much. It's up to you. Okay. Now some properties of the dot product. So if A and B and C in boldface are vectors, and then C here not in boldface is a scalar, then the following is true. So the first one actually very useful. A dotted with itself is equal to the magnitude of A squared. Make sure you can verify that to yourself, because this is something that we're going to refer to several times throughout the course. Also, the dot product is commutative. So A dotted with B is equal to B dot A. That's property 2. Property 3, you can distribute the dot product over addition. Property 4, the associative property holds, as well as, here notice the commutative property. And then for 5, if you dot the 0 vector with A, you get back 0, the scalar. Now we're going to do a proof of property 4, and you should be able to prove all of the properties here in this box, 1 through 5. And so I'm going to work through an example of how to do a proper proof. So let's let C be any real number, some scalar, and vector A I'm going to define to have components A1, A2 up until A sub n, and vector B has components B1, B2 up until B sub n. Okay, so I want to prove, I'm just going to actually focus on, let's say, this first equality right here, that first statement. Okay, so I'm going to begin with C times vector A dotted with B, and now I want to show that that equals C times A dotted with B. Now, if you haven't done too many proofs, then maybe the process is going to be a little foreign to you, but just make sure that you don't skip any steps. It's a proof, so we know the result is going to be true, right? We know we're going to end up with the equality statement there, but when you're doing a proof, the burden is on you to justify each step and why it's valid. So C times A, I'm just going to refer to the component form of A and B that I have above. So I have C times A1, A2, up until an, dotted with b1, b2, up until bn, okay? And then from here, the next step that makes sense is I'm going to distribute c, the scalar, across that vector A. So I have CA1, CA2, up until CAN, dotted with B1, B2, up until B sub n. Okay, what allows me to do this? Well, this is basically scalar multiplication. Okay, you don't have to write the reason off to the side, but it's a good idea, especially if you don't have a lot of experience writing proofs, because what it does is it keeps you accountable and it stops you from skipping too many steps in each line of your proof. Okay, what would we do next? Well, we would just apply the definition of the dot product. So we would have CA1B1 plus CA2B2 plus up until CA sub n, B sub n. So this is the definition of the dot product that we're just directly applying. And remember, our goal is to have C times the quantity in parentheses A dotted with B. So what am I going to do now? I'm going to factor out C. So I'm going to take out C, and I have A1B1 plus A2B2 all the way up to A sub n, B sub n. And what allows me to factor? Well, I'm just applying the distributive property in reverse. So this is the distributive property. And then lastly, I'm going to apply the definition of the dot product again. So I have C times vector A dotted with vector B. And that's the definition of the dot product. Okay, so take some time to make sure that you can do a proof for all of the remaining properties of the dot product. Okay, now we're going to focus on other applications of the dot product. So what I want you to do is consider two position vectors A and B. We're going to sketch them along with the vector A minus B, and we're going to call theta the angle between the two vectors A and B. Okay, so I'm just going to draw them in the first quadrant. They're position vectors. Theta is the angle between them. I'll just draw them in two space. So say vector A goes to here maybe. There's A, then this will be vector B, and then I have to sketch the vector A minus B. Well, we know we can just use our triangle rule, and then here is vector A minus B. Okay, theta is the angle between them. Got it. Now, I can apply the law of cosines, right? And remember what the law of cosines tells us, that the length of the side opposite the angle squared. Well, how do I say the length of that side? The length is going to be the magnitude of A minus B squared. The length of that side squared is equal to the sum of the squares of the lengths of the other two sides of the triangle. So that would be the magnitude of A squared plus the magnitude of B squared minus 2 magnitude of A magnitude of B cosine theta, right? We have that by the law of cosines. Now what I want you to do, we're going to put that on the back burner and focus on something else. Remember I told you in the previous slide about the properties of the dot product to remember that the magnitude of a vector squared is equal to it dotted with itself. So this means that the magnitude of A minus B squared is equal to A minus B dotted with A minus B. Now I want to expand this expression, okay? And remember, we know that the dot product is distributive. So I'm going to have A minus B dotted with A minus A minus B dotted with B. Distributing once more, I get A dot A minus B dot A minus A dot B plus B dot B. Okay, and then here A dotted with A, that's the magnitude of A squared plus, here is magnitude of b squared, and then I have minus 2a dot b. Okay, well remember the expression I told you to hold on the back burner? That was also equal to magnitude of a minus b squared, correct? So I can set them equal to each other, meaning I can set this expression equal to this expression. What will we have if we do that? All right, it's time for a little zoom in so we have some room. So then we're going to get magnitude of a squared plus magnitude of b squared minus 2 magnitude of a magnitude of b cosine theta is equal to magnitude of a squared plus magnitude of b squared minus 2a dotted with b. And notice we can cancel out quite a bit of stuff. We can cancel out the magnitude of a squared, we could cancel out the magnitude of b squared, as well as that negative 2. So what are we left with? We're left with the theorem below. And the theorem tells us if theta is the angle between two non-zero vectors a and b, then a dotted with b is equal to the magnitude of a times the magnitude of b cosine theta. Okay, voila, very exciting result using the law of cosines and one of the properties of the dot product. Now, what you're probably going to apply even more throughout the rest of this course is the following corollary. So if theta is the angle between two non-zero vectors a and b, then just rearranging the theorem above and solving for cosine theta, we know that that's equal to a dot b over magnitude of a times magnitude of b. And the great thing about this corollary is, remember, cosine inverse's range is from 0 to pi. So you'll definitely get the correct value of the angle, even if it is obtuse, where that's not the case, remember, with sine inverse. So this holds for theta between 0 and pi. Okay? And I would say the majority of the time that you need to find the angle between two vectors, you're just going to apply this corollary directly. So here we go. Let's look at an example. Find the angle between the vectors 7, negative 2, 1, and 1, 0, 4, and then round to the nearest tenth of a degree. That's 1 decimal place. Okay, so we're going to have cosine theta is equal to 7, negative 2, 1, dotted with 1, 0, 4, over the magnitude of each of these vectors. So I'm going to have square root of 49 plus 4 plus 1 times the square root of 1 plus 0 plus 16. And then remember, we computed this dot product previously, so it's actually 11 divided by the square root of 54 times the square root of 17. And then from here, just use your calculator. So theta is going to equal cosine inverse of 11 over the square root of 54 times 17. You can put them underneath the same radical. And then make sure you're in degree mode. That's approximately 68.7 degrees. Okay. Good. Now moving on, another useful definition, we say that vectors A and B are orthogonal if and only if A dotted with B is equal to 0. Okay? Orthogonal you can think of as perpendicular, but it has a lot more nuances in the definition. For example, the following. Note that this definition implies that the 0 vector is perpendicular to all vectors which is why in the previous lesson we said that it has all directions, right? Which seems kind of strange. You would think it has no direction, but technically since it's orthogonal, it's perpendicular, to every single vector, then it takes all directions. Okay, and this is the easiest way to check now if two vectors are orthogonal. So what you would do is you would take their dot product And if their dot product comes out to be 0, then you know they're orthogonal. So let's determine whether the following two vectors, 4, 1, 5, and negative 2, 3, 1 are orthogonal. So 4 times negative 2, that's negative 8. 1 times 3, that's 3. 5 times 1, that's 5, and that equals 0. So yes, they are orthogonal. Okay, so that's the easiest way to check. Okay, new definition. If A is a non-zero vector in V sub 3, V sub 3 means three-dimensional vector space, then the direction angles of vector A are the angles alpha, beta, and gamma, which the vector A makes with the positive x, y, and z axes respectively. Okay, so vector A, say it has components A1, A2, A3. Okay, and if you wanted to figure out what the angle was that vector made with the positive x, y, and z axis, then you would be finding those direction angles, alpha, beta, and gamma. Now the direction cosines of A are the cosines of the direction angles, and we can use the corollary on the previous page to find those. So cosine of alpha would be A dotted with, well, what vector would we use to represent the positive x-axis? So let's just throw up a little sketch here, right? There's our z-axis. Here's the x-axis. Here's the y-axis. So what vector would you want to use to represent the positive x-axis? Well, you have a lot of options. The nicest one is to use I hat, right? Wouldn't you just want to use 1, 0, 0? So I have A dotted with 1, 0, 0 divided by magnitude of A, and I hat is a unit vector, so its magnitude is 1, which you can clearly see. Oh, and then I'm going to end up with, if I take A and dot it with 1, 0, 0, only the first component's going to survive. So in the numerator, I'm going to have A1 over magnitude of A. And then similarly, what would cosine of beta be? Well, you'd have A dotted with 0, 1, 0, so only A2 would survive in the numerator over magnitude of A. And then lastly, cosine of gamma, you would have A dotted with 0, 0, 1, so you would be left with A3 in the numerator over magnitude of A. All right? Very good. Now notice if I have cosine squared alpha plus cosine squared beta plus cosine squared gamma. So if I square all of these direction cosines, I'm going to have A1 squared over magnitude of A squared plus, that's this guy, and then cosine squared beta is going to be A2 squared over magnitude of A squared plus cosine squared gamma is going to be A3 squared over magnitude of A squared. They all have the same denominator. It's magnitude of A squared. And I have A1 squared plus A2 squared plus A3 squared. And lo and behold, what is this all in the numerator? That's the magnitude of A squared. So I have magnitude of A squared divided by magnitude A squared. That's just 1. Dun, dun, dun. So the sum of the squares of all of the direction cosines are going to be 1. It's going to be 1. All right. Interestingly, if we want to write out a unit vector in the direction of A, remember we discussed, you want a unit vector in the direction of A, you take A and divide by its magnitude, right? And A has components A1, so you would have A1 over magnitude of A, A2 over magnitude of A, A3 over magnitude of A, and each of these components are the direction cosines. You have cosine alpha, cosine beta, and cosine gamma. So the direction cosines are the components of the unit vector. All right, good. So let's look at an example. It's pretty straightforward application. Find the direction angles for 3i hat plus 5j hat minus 4k hat. Okay, if you want to rewrite your vector using the other notation, that's totally fine. So we have 3, 5, negative 4. I also need the magnitude of a. So that's going to be the square root of 9 plus 25 plus 16. So that's going to be, let's see, 34 plus 16, that's 50. So that's going to be 5 rad 2. Okay, so cosine alpha is equal to, we know a1 over magnitude of a. So that's going to be 3 over 5 rad 2. And I'm not going to clean it up further because I want the actual direction angles. I want alpha. So that means alpha equals cosine inverse of 3 over 5 rad 2. And we'll just round to the nearest 10th place again like last page. So we have 64.9 degrees. And then similarly, cosine beta would be 5 over 5 rad 2, which is 1 over rad 2. And don't you dare reach for your calculator. You should know that means beta is equal to 45 degrees. Yes. And then lastly, cosine gamma is negative 4 over 5 rad 2. So that means gamma is, you can grab your calculator now, don't worry, cosine inverse of negative 4 over 5 rad 2, which is about 124.4 degrees. Okay, there they all are. They look sloppy. If you're taking a test, don't drive your instructor crazy like this. Write them out nicely. Okay, and alpha is 64.9 degrees. Good. All right. Now we're going to move on to a very important example. Projections. Okay. So to begin our discussion of projections, we're going to look at two vectors here, A and B, and they have the same initial point P. What we're going to do is drop a perpendicular from R, which is the terminal point of vector A, to S. So this is a 90-degree angle here. And what we want to do is find the length or the magnitude of PS. Okay, well, in order to do that, I'm just going to use my right triangle trigonometry. Okay, I know that cosine of alpha is going to be the ratio of the adjacent side over the hypotenuse. Well, the adjacent side of this triangle is the magnitude or the length of that side, PS, over, well, the hypotenuse, this is vector A. Its length is going to be the magnitude of vector A. So that means PS, the length of PS, is equal to magnitude of A cosine theta. Now think back to what we just talked about, that corollary involving the dot product. And we know that cosine theta is equal to the dot product between the two vectors that contain that angle divided by each of their magnitudes. So I'm going to replace cosine theta here, okay, with the definition from the corollary. So we're going to have A dot B divided by the magnitude of A times the magnitude of B. And notice now I can cancel out the magnitude of A, and so I'm just left with A dot B divided by B, magnitude of B. Okay, and so this is the definition for the scalar projection. The scalar projection of vector A onto B is given by the component of A along B. Okay, so whatever you're projecting along, that's the subscript, and then the vector that you're projecting is in normal case with where you write COMP. Okay, and this is also called the component of A along B. Okay, and its definition, we have it above. It's A dot B divided by magnitude of B. Okay, and it can be useful to just think of, you take A and then you dot it with B divided by its magnitude, if you like. All right, now this can be confusing for some students. So I think one of the best ways to relate it is if you have a vector and you know how you decompose it into its horizontal and vertical components, right? So like say you have this vector V, here's vector V, and then what we do is we're gonna decompose it into, here's its horizontal component, so this is V sub X, and then this is gonna be V sub Y, shouldn't go out so far, right? So this is basically its scalar component along the x-axis, and this is its scalar component along the y-axis. Now what you're doing when you have the definition here of the scalar projection, you're just taking some vector, in this case we're taking vector A, and instead of finding its horizontal and vertical components, I'm breaking it down and projecting it along any other vector that I choose. So I just want to find what its projection is along this vector here, much like when we find the horizontal component, so the component of vector V along the x-axis. Okay, you're just projecting it along something other than the x or y axes. Now, this is a scalar projection, right? What if I actually wanted the vector PS, the vector projection of A onto B? Well, what would you do? Well, I don't want to mess with its length, right? I want the vector projection, let's go back to the picture here. I want the vector projection to have the same length here as PS, but I just want it to be a vector now. So what would you do? The scalar projection gives us that actual length. Now to make it a vector, if I want to preserve that, I want to send it or multiply that scalar component by a unit vector. That way the magnitude will be preserved in the direction PS. And that's basically just taking B and making it a unit vector. So the process is as follows. So if I want the vector projection, PS, what we do is we write that as projection of A along B, and that would be the scalar component of A along B times B divided by magnitude of B. Remember, we want a unit vector. So this gives us our magnitude. This preserves the length of the projection, the scalar projection, and then this is the direction. We want it in the direction of B. I don't want to mess with the magnitude, so that's why I need a unit vector. And then remember, the scalar projection is defined to be A dot B divided by magnitude of B, and then we have times, now I want it to be a vector quantity, B divided by magnitude of B. Okay? So that's our definition for the vector projection of A onto B. We can clean it up a little bit. So we write the projection of A onto B. You read it backwards from how you write it, huh? Oh well, just get used to it. So this is going to be A dot B divided by, we have magnitude of B squared, right? And then we're sending it along vector B. That's why it ends up being a vector quantity in the end. Okay, so another way to think of this formula is that you basically have that magnitude times the direction, okay, and the magnitude is that scalar projection of A along B, and then the direction that we want is along vector B, but we don't want to mess with the length, so we need it to be a unit vector. Okay? Lastly, we may want to find vector SR, which is the orthogonal projection of A with respect to B. And to do this, we're going to make use of vector subtraction. So I'm going to go back up to the diagram that we have so we can identify where SR is. Okay, so here is SR. And that's the orthogonal projection of A with respect to B. So notice here that vector SR is PR minus PS. So that gives us the following definition here, that vector SR, which is PR minus PS is equal to vector A minus the projection of A along B. Okay, so our definition for the orthogonal projection of A with respect to B is what we have up above. So the orthogonal projection of A with respect to B is A minus the vector projection of A along B. All right, so let's just look at an example. We're going to apply all of these definitions directly. So let vector A have components -1, -2, 2, and then vector B has components 3, 3, 4. So first we're going to find the scalar projection of B along A. Okay, so for B along A, I'm going to take B dotted with A and then divide by the magnitude of A. Okay, so we're going to have here 3, 3, 4 dotted with -1, -2, 2. And then I'm going to divide this by the magnitude of A. So magnitude of A, let's see, I have square root of 1 plus 4 plus 4. So that's 9. So that's going to be 3. And then let's look at the dot product here. So I have the -3 plus -6 plus 8. That's -9 plus 8. So this is -1. So we have -1/3. All right, now what about the vector projection of B along A? Well, I already have the scalar projection. I want to send it along vector A, right? So the subscript is the direction, but I need to make a unit vector. So the more like you talk yourself through this and you understand what the formula is doing, it won't be so arbitrary for you to memorize, right? So I've got my scalar projection. I want to send it along A. I need A to be unit vector, so I need to multiply this by -1, -2, 2. But I got to divide by the magnitude. I want to preserve that length. So divided by 3. So this is going to give me -1/9 times -1, -2, 2. And then distributing the -1/9 through, I get the vector 1/9, 2/9, and -2/9. Okay. What about the orthogonal projection of B along A? Well, you can just apply the definition directly. That's B minus the vector projection of B along A. So that's going to be, vector B was 3, 3, 4, minus the vector that we have up above, so 1/9, 2/9, and -2/9. Okay, and then subtracting from here, so 3, that's going to be 27/9. So we have 26/9. Then we have 25/9. 36 plus 2, so 38/9. Okay. All right. So just make sure you put those definitions to memory. That way you have no problem applying them later on. Now, earlier in your calculus sequence, you should have studied the concept of work. And we saw that work could be calculated as force times distance. But remember, this is only true if the force is applied directly along the line of motion. However, if you have a constant force F and it's applied at some sort of angle, then the work is defined as follows. So the work is going to equal the amount of force that's being applied in the desired direction times the displacement, right? And now that we know vectors, we can refer to D as our displacement vector. And then F is also our force vector. So how would you get the amount of force in the desired direction? Well, I would want to figure out what the scalar projection is of the force vector along the displacement vector, right? That's the direction that the object is moving in. So I want the scalar projection of force along the displacement vector times the actual displacement, that actual distance, so that would be the magnitude of vector D. And remember, our definition for the scalar projection is we have F dot D divided by the magnitude of D, and then I still have this magnitude of D here for the displacement, and so those will cancel out, And I'm left with the definition that probably you've seen before. So work is equal to force vector dotted with displacement vector, which we could also write, since we have our corollary, as F, magnitude of F times magnitude of D times cosine theta, the angle between them. So we're going to look at a very straightforward example of applying this here. We have a wagon, and it's pulled a distance of 100 meters along a horizontal path by a constant force of 50 newtons. And the handle of the wagon is held at an angle of 30 degrees above the horizontal. So how much work is done? So I'm just going to draw a little diagram. So here is our wagon, okay? And then this is our horizontal. And the handle is held at an angle of 30 degrees above the horizontal. So this is a 30-degree angle here. And the force that's being applied is 50 newtons. And it's pulled a distance of 100 meters. Okay, so if I want to figure out the work, I'm just going to take the magnitude of the force times the magnitude of the displacement vector times cosine of that angle, which is 30 degrees. So I'm going to have 50 times 100 cosine 30, that's rad 3 over 2. So I'm going to have 5,000 divided by 2, which is going to give me 2,500 rad 3 joules. All right, so that concludes the lesson on the dot product. Stay tuned, the cross product is coming up next.